Okay, so we're now going to move on. We've got two speakers from Leeds who are going to share some of the ongoing work that's happening within LIFD. So first of all, I'd very much like to welcome Dr. Sepideh Khodaparast. Sepideh is an early career university academic fellow and in fluid dynamics, and is part of the fluid dynamics management team as well. So he's going to talk to us about fluid-driven approaches for precision surface patterning.
Thank you, Kat. So yeah, I joined University of Leeds in 2020, so I'm a bit younger than LIFD, but joined University of Leeds thanks to the LIFD. And I'm going to talk about a bit, maybe not exactly fluid dynamics, but adding physics to a fluid dynamics problem mainly, and especially talking about fluid-driven approaches for surface patterning. So I'm going to go through some ideas. First starting with why do we care about surface patterning in the first place, and why I think fluid-driven approaches might be the right approach for creating surface patterning. So surface patterning has loads of applications, and the applications keep coming up. I just picked up a few different fields where you see lots of surface patterning applications these days, but there's loads of other things around in food industry, in really different fields. But I picked up a few examples in energy, in textile, in biomedical applications, why we care about surface patterning. So in energy, if you're thinking about phase change, especially for heat transfer, for cooling or heating devices, people are starting more and more to use pattern surfaces to induce nucleation, both in terms of condensation and boiling. And there are also new fields for solar cells, for example, for using pattern surfaces for light to energy conversion. So there's, and these are not the only applications which are related to energy. Again, I'm just using some examples. In textile, this has been going on maybe for even longer. So we are interested in creating anti-wetting and super hydrophobic surfaces by adding texture to the textile. And in biomedical applications, this is probably a bit newer. We are after adding surface structures to so most of these applications, they involve the end surfaces which come in contact with fluids. And that's how we started working on these projects, because we were originally interested in how fluids interact with the surfaces. And for biomedical applications, for example, there's this field of anti-fouling materials that surface patterning can induce through changing the boundary condition on the surface and changing it from no slip to slip condition. It could prevent, for example, bacteria from sticking to the surface, or reduce the contact area and reduce the adhesion energy onto the surface, or all the way to directly interact with cells if the dimensions of the surface structure that you have is much smaller than the cells or the bacteria that are sitting onto the surface. So there are all these applications which have been around, and they keep coming up. But there's an issue here. So most of the surface patterning techniques that have become very trendy, and in the past decades, there's lots of research which are going on, which are dedicated to surface patterning techniques. The majority of them, especially when you go to nanoscale and microscale, the majority of the nano fabrication and microfabrication surface patterning were borrowed from electronics. And borrowed from electronics meant that they were optimized for silicon and for solid materials. And they were all top-down techniques that you start with a solid material and you start etching through either chemical etching or mechanical etching. And if I go back through the applications that we have, there are a few major challenges when you think about surface patterning for these kind of applications. So when you think about energy applications, for example, fluid applications where you have heaters or cooling devices, most of these devices are actually not flat surfaces, they're curved surfaces, and might involve coating of the top, the exterior and the internal surfaces. If you think about energy, for example, solar cells, the techniques that you apply should be scalable. You cannot, all of the micro and nano fabrication techniques that I showed you in the last slide, maximum they can reach centimeter scale, while here we're talking about meters of material. If you think about textile, again, there's an issue with the scalability, and these materials are deformable, and it's even more complex, the material. So it's a porous structure, you have multi-scales of starting from how you build a fiber, how you bring all these fibers together. So if you want to make these materials, pattern these materials, how do we apply those? How do we find what's the right technique to apply to bring nanostructures onto these surfaces? Again, biomedical applications is a bit similar to even energy applications. Most of the tools that we have in biomedical applications, there are curved surfaces. You need to coat both internal and external surfaces of these. And if you think about it, across all of these applications, there are lots of materials that the challenge of sustainability goes across all of these different applications. So it's, for example, biomedical application, textile, there's lots of materials that are single-use materials. So whatever technique you use should be inexpensive enough and should be scalable enough that if you use, for example, the image that you see for the biomedical application is a catheter. These devices are single-use devices and they go to waste. So whatever technique you're using, it should be cheap enough, but it should be also sustainable, both in terms of material and the energy that you put into producing that material. So to move on from these top-down methods, there's been lots of good work on the bottom-up methods where you use self-assembly techniques. So this is more of a fluid-driven techniques where you use colloidal material, which are in the fluid phase to create patterns. But most of these techniques, they still involve multiple stages. So you start with for example, a liquid film that has colloids inside. You create patterns through the self-assembly of the colloids, and then you replicate it into another material. So the question that we had was that when I was talking about all of these applications, I kept talking about surface patterning as a coating problem. And the coating problem, we knew it as in the fluid dynamics of coating. We know lots of coating strategies for different types of material. We know how to coat curved surfaces. We know how to coat porous materials. Assuming that we know all of the physics of the coatings and the fluid dynamics of the coating, could we do this one single process where during that coating process, we could induce some phase change, so adding physics to it, some phase change, for example, condensation or crystallization in the material that we are coating to create patterns as the coating is being produced. So in this talk, I'm just going to assume that we know all the physics of coating for different materials, but add this phase change to it. I'm not going to talk about condensation. Francis in the audience has a poster on condensation, how we can create patterns on the coated material using condensation, but just go through crystallization. And crystallization is kind of stochastic processes, how we can make them more deterministic. So how we can use this crystallization to create patterns that we can sort of predict, both in terms of the properties of the pattern, but also the functionality that we want out of it. So one of the masters in terms of when we think about surface patterning, micro and nanostructures are the plants. And plants have a wide variety of different patterns across. I'm going to show you, skip to the functionalities that they produce. So they can be all of these micro and nano patterns. They go across larger areas. They can be, for example, in terms of wetting, slippery, or sticky. And most of these functionalities, the change in the functionality is a small tweak to the chemistry of the surface structure that you see, but mainly the physical topography of the structure that you see. And so as I mentioned, the design of these micro and nano surface structures, for example, in the slippery surfaces, you have hierarchical structures with micro and nano structure features, while in the sticky designs, you have larger structures that allow air-liquid interface to infiltrate in. So from the great works of the plant biologists, we know that all of these structures which exist on the plants are made of waxes, and they're crystalline structures of waxes. And there's been loads of good research in by plant biologists where they picked up different surfaces of these are early days where scanning electron microscopies were just coming up. So in 1960s and 70s, so they scanned loads of surfaces of different plant waxes and extracted them, recrystallized them, and they could get more or less similar structures. So question is sort of, at this point, we knew that the chemistry and the physical topographies are linked. And the questions that we had is, like, if you pick up the right chemistry and focus on these kind of waxes, can we tune the physical topographies? And so to find the right waxes, you can go extract it from the surface of the plant leaves, but that's not exactly sustainable. So we started looking at waxes which are already available, and especially looking at rice bran wax. I'm just gonna go a bit faster through this slide, but why rice bran wax? So we use loads of white rice, but rice is not exactly white. So we get rid of lots of coating of rice to get to the white rice. And part of it is the rice bran. And the rice bran, even though it's only 8% of the rice seed, for example, there's the data here in 2014, 2015, the rice bran production is nearly 24 million tons worldwide. So, and majority of it, some of it these days is used to create oil from rice bran, but when you produce the oil to purify it, the rice bran wax comes out of it, which goes to the waste. And the idea was, can we do something with this waste material? So again, you can, these waxes are solid at room temperature, most of them. And if you heat them up, they melt, they become a liquid. You can use them for coating and then solidify them to get a coating, a solid coating. And most of the time when you melt them and cool them, you get these kind of surfaces which are relatively smooth with some wrinkles. But if you dissolve them in solvent and evaporate the solvent, then you start getting these very nice surface structures. And these surface structures are quite predictable. So you can, for the same chemistry and the same solvent and the same thermodynamic conditions, you always get the same structures. And you can see that the wetting conditions, especially in this case, going from a rather smooth phase to a more textured surface with higher roughness, you go from relatively hydrophobic to almost super hydrophobic surfaces. And the question we had here was, okay, we know that adding solvent creates texture, but can we control that texture without changing the chemistry of the wax? And the answer is yes. So it's really a thermodynamic question. Depending on the saturation level that you have, you can change the solvent, for example, in this case, and go from larger structure to smaller structure that allows you to go from hydrophobic to super hydrophobic surfaces. And it's not only the static condition that's changing in there. The surface goes from surfaces which are very sticky, so they hold on to water and liquid substances, to slippery, and all of this comes from the surface structure. So all of these materials that you're looking at the bottom, although they have different wetting behavior and interaction with the fluid media, they are made of the same exact chemistry. So basically we go from scenarios which are like the one that you see on the left, scenarios which are on the right. And so I showed you some examples briefly from rice bran, but you can reproduce this following the same thermodynamic principles, going to different kinds of waxes which are sourced from different materials, and you get similar structures. So all the time when you use solvents that are evaporating faster, that allows you to reach deeper supersaturation levels, you get smaller structures that gives you super hydrophobic slippery surfaces, while the surfaces which are made out of toluene, which is a very slow evaporating solvent and lower saturation level, it gives you hydrophobic but sticky surfaces. And so I mentioned the challenges in producing coatings. These are the coatings that we made with using the waxes, but through solvent evaporation. So you can coat inside the tubes, inside and outside the tubes, the first image as you see on the top. Similar things you can do with the fabrics, for example. So the images on the right are the fabrics, the native natural fabric. On the left, you see that through these coatings with the wax that is dissolved in the solvent, you can actually coat the individual threads and fibers in the fabric. So these techniques are really nice because you start with a fluid that's isotropic, so you can sort of apply most of the knowledge that you have on the coating, I don't know, dip coating, spray coating, and just add this bit of the phase change into it. So these are the smaller scales that
on the left, you see the smaller scale electron microscopy images. On the right, you see that the functionality that we had going from slippery surfaces in the center, that the water droplets, which are dyed here, they tend to be quite spherical and they roll onto the surface. So you see different materials, for example, which are coated aluminium rod, cotton pad, felt paper, and wood coating. And you can go from slippery to sticky. So all the way, it works all the way from smaller scales to functionalities that are in larger scales. And I think I'm sort of done with my talk. And I believe these materials, the waxes, they provide us with the right sustainable material. It's quite affordable, so we can think about larger scale fabrications, and we can tune these, not necessarily the chemistry of the material, but tune the thermodynamics of the coating and the thermodynamics of the phase change that's happening during the coating to get the functionality that we want out of it. So with that, I would just like to thank LFD and the rest of the funders that funded this research. And thank you very much for listening.